Hello, good morning, everybody. It is my great pleasure to welcome my colleague and collaborator, Francesca Arici. We have two papers together, right?
Yes.
If I remember correctly. Francesca did her PhD in 2015 in CISA, Trieste. Then she was a postdoc in Max Planck Institute in Leipzig. And now she is an assistant professor in Leiden in Netherlands, where actually she is the node coordinator of our huge European network. And I will tell you more about our network in my afternoon talk for local students. So please wait till then. Francesca I can assure you that it's a great pleasure to do mathematics with her. I know it from my own experience. But also I would like to mention that she is an extremely good lecturer. I mean, her lectures are model lectures. If you want to learn how to give a talk in mathematics, just go on YouTube and see one of her talks. Also, she is remarkably good in public outreach, like Soren Elias, who gave a talk 2 days ago. She is a master of public outreach, and her social activity in order to reach out to people who are not mathematicians are truly commendable. And now, Francesca, you have another opportunity to do outreach to people. There are many young students, undergraduates, so they are not students of non-commutative geometry, so your task is to seduce them into non-commutative geometry. And please bear in mind that their background is not that of non-commutative geometry, so you should speak to them like to your daughter. Okay, Francesca, the Zoom is yours. Take it away.
Thanks a lot. Let me share my screen then. So here it is, and I will also view full screen. So thanks for the introduction, and also, yeah, it's not an easy task to give this talk, so I hope I will not disappoint the audience, especially given the introduction that was made just before. So, so this is the title of my talk. You may have read it already on the program. It's the unreasonable effectiveness of operator algebras, and in bridging between geometry and quantum theory. Now, some of you may recognize that this is a citation of an article from many years ago. This is an article from the 60s, 1960, by Eugene Wigner. It's an American-Hungarian physicist. So he wrote this piece that was kind of not really a physics paper, neither a mathematics one, more a philosophical paper. And the title of the paper is The Unreasonable Effectiveness of Mathematics in the Natural Sciences. So in this article, Wigner argues that the way mathematics works as a language to describe physics is quite striking. And one sometimes has the feeling as if you are walking around with a bunch of keys, and every time you have to open the door, the first key you try works. And then you start wondering if there's something weird with the keychain you got, because it works too well for opening all the doors you encounter. And something like this is what happens in mathematics. You often have the feeling that the language of mathematics works too well for describing physics, and even concepts like complex numbers that don't seem to be motivated by reality turn out to work very well in physics. And one of the examples, speaking of complex numbers, is what he calls a miracle. It's the success of the axioms of quantum mechanics, the way they're formulated by Dirac. So if some of you have been exposed to quantum mechanics before, you know that there are various approaches. There's Schrödinger formalism and the Dirac formalism. And in this particular article, Wigner focuses on the Dirac one, which is the one based on the language of linear operators on Hilbert spaces. So I will say more about this in a second. But this is somehow the motivation of my talk, but also of my research. What we do at the end is operators on Hilbert spaces. You will see why. And this should give you an idea of what kind of research we do in operator algebras. So now let me move forward to quantum mechanics, which is indeed the motivation of this talk, but also the motivation of this unreasonable effectiveness that Wigner was talking about in his essay. So quantum mechanics, well, I put the cat. I also wanted to put the dead cat, but then I thought it was a bit gruesome. I put this cat because of the famous Schrödinger cat paradox. So you all know that quantum mechanics and cats go together. So quantum mechanics is probably one of the most experimentally successful physical theories, in the sense that the formalism that I just mentioned, the Dirac formalism, allows you to make very accurate predictions about the measurements that you can do in quantum mechanics. And it is a theory that works at the atomic and subatomic scale. So it doesn't really work in the classical regime where we live now, but it has effects, of course, on our classical world when you, how do you say, you combine quantum effects and classical effects. And this leads to paradoxes like the one of the cat. So if you put a decaying atom, which is something that behaves according to quantum mechanics, and in a box with a cat, then the fact that the cat could be alive or not, depending on whether some poison mechanism, depending on this atom, turns on or not, is something macroscopic on which the microscopic world has an effect. So this leads, of course, to paradoxes, but in general, the theory works at the atomic and subatomic scale. And the reason why this theory was developed in the early 20th century was to explain observations in various experiments that couldn't be explained with classical physics. So the first one was the black body radiation. Then you have this famous double slit experiment where you throw a bunch of electrons through a double slit and you get a very interesting pattern at the other side. And then, of course, the photoelectric effect. So the fact that materials that are illuminated emit electrons only at with certain energies. And this is actually what this explanation of the photoelectric effect using quantum mechanics, or a precursor of quantum mechanics, maybe due to Einstein, is what got him the Nobel Prize. And this is often a misunderstanding. Many people think that Einstein is only a relativist, so he developed our general relativity, but actually got this Nobel Prize for the work on quantum mechanics. And he was also one of the people that had the most trouble with all the implications of quantum mechanics. But in general, this theory would really arose by the attempt to apply what was known up to then, classical mechanics and thermodynamics, to very weird phenomena that happened at the subatomic scale and where our knowledge wasn't enough. And the way to solve these issues, and these are basically the features and also axioms of quantum mechanics, is to assume that in the quantum regime, physical quantities like energy, angular momentum, assume discrete values. And this is what it means to be quantized. So the possible values that these quantities can assume are multiples of a fixed fixed value. And this is exactly the word quantum. You see here the hydrogen atom. I will say that relates to my third or fourth point more. So there is another important feature of quantum mechanics, which is also quite hard to grasp, which is a particle-wave duality. And the idea is that the quantum mechanical objects have a behavior that obeys both the rules for particles, so points, as for waves. So the waves like sound and waves in water, and so the particles from quantum mechanics seems to behave sometimes as particles and sometimes as waves. And this is well exemplified by the double slit experiment, where we see patterns that are wave-like when we throw a ray through a double slit. The other interesting feature of quantum mechanics, and which is also something I will focus on in a bit, is what is called the uncertainty principle. And this is a general principle of quantum mechanics that tells us that there are limits to how accurately we can measure the values of physical quantities. And to be precise, it has to do with measuring the values of two physical quantities in a particular, for a quantum system in a particular state. There are quantities that can be measured with arbitrary precision, even more several quantities, but there are also combinations of quantities that cannot be measured with arbitrary precision, which leads us to either measuring one of the two with very good precision, and then inevitably the precision in the measurement of the other quantity will decay. The final aspect of quantum mechanics that makes it so special and that makes it also break with previous versions of physics, although this is somehow a feature that thermodynamics has as well, is that quantum mechanics is probabilistic in nature. So you cannot make precise predictions, exact prediction. You can only give probabilities. So you can say, if I perform a certain experiment, the probability that I get this value for the measurement is blah and blah. And this you can see also here in this picture of the hydrogen atom. So those are the orbitals for in the hydrogen atom. And they give you a probability of finding an electron. So where you see black, there's probability 0 of finding the electron, and we see very bright, there's probability almost very high probability of finding the electron. So you cannot know how the orbit of the electron looks like. This is something deterministic, but you can know where it's more likely to find the electron if you would measure their position. And this is this breaks with all the classical physics or Newtonian mechanics. So, and this also means that when you repeat experiments, you don't always get the same result, which is some feature that classical mechanics doesn't have. So this is a theory that has a lot of weird features, as you see, and it turns out that there is a natural way of describing this. But before of doing that, I would want to stick a bit more to the question of the uncertainty principle. So in the uncertainty principle, there's a particular instance, which is the one for the momentum and the position of a particle. And basically, this is what is, when you hear talks, general communication, science communication talks about quantum mechanics, or when you read about quantum mechanics online, or you hear about that in movies like Transformers, they talk about quantum mechanics at some point. The idea of this uncertainty principle is that it's often formulated for two particular observables, which are the momentum and the position of a particle. So basically where the particle is and how fast it is moving. And the idea is that you cannot measure both those quantities with absolute precision. The idea is that the more accurately, and this I already explained before, the more we get precise with one of those variables, say the position, then inevitably we have to give up some precision in the measurement of the momentum and vice versa. And this you can formulate in mathematical terms by saying that the variance, so this is this symbol here is the variance of the thing we measure, in this case of the momentum and of the position. The product of the variances is bigger than something, which means if I make something very small, then if I make delta P very small, then inevitably delta Q will increase, and vice versa. If I make delta Q very small, then inevitably delta P will increase, because their product has to be bigger than a certain quantity, which in this case is this H divided by 4 pi, and H here is the Planck's constant due to Max Planck. So it's in the order of 10 to the minus 37. So it's a very small number, but still it's not zero.
Excuse me, may I have a question?
Yes.
What's the definition of measurement?
Well, can you be more precise to what kind of definition do you want? The mathematical definition, or?
I mean, because it's, are we talking about like scientific measurements with some specific, no, in some specific environment, or is it just every interaction with some external system a measurement?
Well, I mean, it could be, well, the interaction is quite tricky. Even if you don't have interaction, you still have this indetermination, this uncertainty, if that's what you're after.
Yes, it's just like, it's the term, how to say it? Like, does it, this uncertainty manifests itself in every interaction, including the quantum particles, or is it seen only from the macro scale? No,
this is really for a quantum. So if you want to measure the position at the quantum scale, so in very small distances, at the moment you try to measure these two quantities, P and Q, you will see why these two have this feature. then you have to give up on the accuracy of one or the other. But we're talking about a microscopic scale. It's not macroscopic.
Francesca, may I comment?
Yep.
So you see, this is actually a mathematical theorem, this uncertainty principle. It's a consequence of non-commutativity. So basically, by the sheer fact that we assume.
It will come in a couple of slides.
Okay, you'll count it. Okay, good. Because I think that maybe that's what he wanted to hear.
Okay, sorry. Then I misunderstood. I thought it was really about the physical setup. Because sometimes when you hear about quantum mechanics, they tell you, yeah, of course, when you want to see where the particle is, you throw light at it and the electron interferes. The photon interferes with the particle and changes. But it's not really like that. It's really, even if you were to design an experiment where there is no interaction from outside the system, you would still get this. So it's not a problem of how we measure. It's really intrinsic. So this is my next point indeed. So it's not that our measuring devices are wrong or don't measure well enough. It's really intrinsic. Even if we had perfect measuring devices, we would still have to give up some precision in the measurement. And this is something that is common to many phenomena that we cannot explain classically, like indeed the behavior of electrons or other particles, both the subatomic and the atomic scale. And as Piotr said, indeed, this is a mathematical theorem. So this follows from from a combination of a result and the other theorems. There is something similar, though. There is an uncertainty principle in the classical world, and this is the uncertainty principle that you have in wave mechanics. So if you think of a wave, of a sound wave, if you have a small variation in momentum, this means that the frequency is quite constant. You have few wavelengths, so it's a sound that is quite pure, for instance. Then the particle is everywhere. You see it, the wave is everywhere. You see it here. There's a very regular sound here depicted, and this wave has a small variation in momentum, but the position is everywhere on the real line. Indeed, the other way around also happens. If you have a large variation in the momentum, which means that your wave is a superposition of several waves, then you can create a wave that is localized in a precise point in space. But indeed, you have to give up something, and that's the precision on the momentum, because then you will have a big variation in momentum, because in order to get such a shape like this one, you need to use many modes in your Fourier expansion, if you're familiar with that concept. And then there is a middle wave. So you have some variation in momentum and some variation in position. That's a wave that looks like the middle one. And there the wave is neither localized nor delocalized. And at the same time, the frequencies also change. So this is an uncertainty principle in the classical world. It's for waves. And if we think about it, we said before that particles in quantum mechanics behave also like waves sometimes due to the particle-wave duality. And it's a consequence of the mathematics that describes waves, that is also presenting itself in the quantum world when we look at our quantum objects as waves. So let me now move to the more mathematically sound description of quantum mechanics. So as I said in this essay by Wegener, there was some stress on the fact that one of the miracles of the effectiveness of mathematics is quantum mechanics. And in particular, he mentions the Dirac-von Neumann axioms. And I see that there is a comment about the uncertainty relation, and indeed, I don't read the name of the person that wrote it, but that Rudin is good reference. So in this Dirac-von Neumann axioms of quantum mechanics, we describe mathematically the theory. And I'm put von Neumann in brackets because this is not really von Neumann's formulation. We see von Neumann's formulation later. This bear, no, it's a cat. Sorry, the cat really likes operators, but it will come in a second. So in the Dirac version of the axioms of quantum mechanics, state of the quantum system, so state as in what does our system look like, can be described by what is a unit vector in a Hilbert space. And
Sorry,
this
may I have a question?
Yes.
So is there any physical significance in states which do not come from vectors in Hilbert spaces or from density matrices? I mean, non-normal states.
I don't know if I'm the right person to answer this.
It's like a state in general sister algebra.
No, that's of course sure, yeah. But then you will see that this is the formulation that von Neumann has of quantum mechanics. So yeah, in his formulation, it's state is a state on a sister algebra.
Mm-hmm.
So that's there is significance there. And then of course, these particular states that I'm describing here give you states in sister algebras by a very easy assignment, which is the equation in the last point of.
Since I was a little bit confused by this, since if you start with a state which is non-normal, okay, so this does not come from a genuine vector or event density matrix, but still you can perform the GNS construction and then the state becomes a vector state, but on this GNS Hilbert space. So I don't know whether physicists are interested in this construction. Is there any?
I think that's how you do axiomatic algebraic quantum field theory, actually, but I'm not an expert of that field, so maybe it's not right. I think it's a very good question.
I think that in algebraic quantum field theory, people would like to somehow avoid the choice of the representation. Somehow this whole net of von Neumann algebras should somehow contain information about all possible representations.
Yeah, that's correct.
Okay,
Yeah, so
you.
I think that, of course, you can do with, yeah, I mean, yeah, I think you can still make sense of such states, but I don't know whether they have a real physical interpretation. So if you can describe interesting quantities like that.
Okay, thank you.
You're welcome. So indeed, a state for the system is a unit vector up to scalar multiples. So you assume that the state in which the system is can be described by the assignment of a vector in Hilbert space. And this vector has to be of length 1. So it's determined also up to a phase. And then the observable of your system in the Dirac formulation are self-adjoint operators on this Hilbert space, and they may be unbounded in this setting. Now, when you want to perform a measurement, you're interested in what the expected value is of your measurement. And for such an observable A, such a self-adjoint operator, and for the state psi, the expected value of the observable in that state is the inner product of psi with a psi. So you apply the operator to your state, and then you take the inner product with the state. And of course, here, the fact that A is self-adjoint makes that the quantity that you get out of this inner product is a real number. And that's what we are interested in, because we measure real numbers. We don't measure complex numbers. So as I said, there is a different formulation of these axioms by von Neumann that uses sister algebras and states on sister algebras. I will say more about this in a while. But for now, these are the standard axioms of quantum mechanics, as you find them in many books like Sakurai or other foundational books of quantum mechanics. So to be fair, at the beginning of the whole story, quantum mechanics was called matrix mechanics. And this was developed by Max Born, Werner Heisenberg, and Pascal Jordan. And they assumed that those observable were matrices and behaved like with the rules of matrices, and then this easily was extended to the world of linear operators. So in particular, if we want to talk about this uncertainty principle that we have mentioned before, if we look at P and Q, these self-adjoint operators that represent the position and momentum of a particle, we have that when we compute their commutator, this is this object that I wrote here, we get that this is different from 0. And this is such an important fact that it ended up on the grave of Max Born. And it's a fundamental feature of quantum mechanics. And it has as a consequence the Heisenberg uncertainty principle that I showed you before. And this was observed by the physicist. Oh, sorry, I wanted to remove something else. The physicist Kennard in 1927. This was an American physicist that spent some time in Göttingen and working in Bohr, Heisenberg, Jordan. And he observed that this uncertainty principle actually follows from the non-commutativity of the two operators P and Q. And the way this works is not on my slide, but I can quickly sketch for you the way it works. Because you have these two operators that do not commute, you can apply important identity that you have in Hilbert spaces, which is the Cauchy-Schwarz inequality. If you're not familiar with the Cauchy-Schwarz inequality, you should think of that as something that kind of generalizes the Pythagorean theorem in Hilbert spaces. And when you apply the Cauchy-Schwarz inequality to the variance of the position and the variance of the momentum, what you get is indeed that you satisfy this equation here, that the product of the variances is bound below by a number, h divided by 4 pi, and this h divided by 2 pi is this, precisely this barred h that I wrote in commutation relation here. So really, the fact that we have the uncertainty principle, or if you want, the fact that we cannot measure with arbitrary precision two quantities, position and momentum, is really a consequence of those commutation relations. So the fact that these two operators, when composed in two different ways, don't give 0, reflects itself in the fact that the corresponding measurements are not possible with arbitrary precision.
Francesca, maybe it's worth mentioning another consequence of this commutation relation,
Mm-hmm.
the fact that these two operators commute to 1. Well, so for starters, you see that they cannot be matrices because the trace of the left-hand side is 0 and the right-hand side is not 0. But it's a more involved exercise to prove that they actually cannot be bounded operators.
Yeah,
so
that's correct.
It's a very beautiful exercise in system.
Yeah, so it's very easy to prove that they cannot be matrices indeed, and because of the trace, and also they cannot be trace class operators for the same reason. But then there is another way, a bit more, it's an exercise in sister algebras indeed, to prove that they cannot be bounded. Very true.
Sorry if I can comment. So in fact, in Rudin's book, there is a proof that this relation cannot be satisfied in any normed algebra, even if it's not complete. Yes.
That's correct. Yeah. Yeah, because that's what it uses, is the norm that you have in the algebra. Sorry, I went back too much. Okay. So now what I just said is actually independent of the fact that these two operators are the position and the momentum. And it actually relies on a series of facts. So the first fact is that their operators are Hermitian. Then that they do not commute, so that you have that their commutator is equal to some constant. And then if you have something like what they wrote here, then you automatically have, by the Cauchy-Schwarz inequality, that the variances are bound from below. So whenever you have two operators that commute up to I times the identity, then you get that their variance must, the product of their variances must be bigger than 1/4. And then, of course, if you have different values of the commutator, this uncertainty relation changes. Like before, we had this H bar. And this is what Kennard said in a, Kennard is American, and I'm getting in a German accent here. In his article, he said, in alle Fälle kann man, okay, I will try to translate this for you. In any case, for those that don't speak German, in any case, we can claim that the precisions of measurement by, that the measurement precision, by such measurements happening at the same time for two variables that are canonically conjugated, which means that they satisfy a commutation relation like this one, will always give a relation between the variances like of this form. So he proves it in this paper. He shows that it's a consequence of the non-triviality of the commutator, and that's really an intrinsic feature of non-commuting variables in quantum mechanics. So it's not really for particles and for a particle position and particle momentum, it's for any pair of canonically conjugated variables. So for instance, this also happens if you want to measure the angular momentum of a particle in different directions, you also have something along those lines. And this is really an exercise in operator theory, or a result in operator theory. So it really depends on the fact that we are in the world of possibly unbounded operators on Hilbert spaces, and that composition of operators is a non-commutative operation in that world. And the non-commutativity gives us this intrinsic feature of quantum mechanics, which is the lack of arbitrary precision. So I will now move to something a bit more technical, which is more the type of mathematics that I work on, and that some of the people that you've seen in this week work on. So I know you've heard several talks about this subject. And I think that you heard also talk by Michael Eckstein on that involved some index theorem. He introduced you to the concept of a spectral triple. So there will be some of this coming back in this part of the talk. Now I will talk about something completely different. I will just talk about topology. So I will look at the topological space. I will assume that it's compact and Hausdorff. So it's very well behaved topological space. And I will construct a set. Now it's just a set. It turned out to have many more properties. I'll look at the functions on this space that takes complex values and that are continuous with respect to the topology. And this set is actually much more structured. It is a vector space. First of all, you can sum and multiply by scalars. So if you take two functions f and g and one scalar lambda, then the function lambda f plus g in point x as the value that is it's lambda f of x plus g of x. So you use the vector space structure that you naturally have in C and that you can use because you have the values of this function to define a new function, and this function will be continuous. And this space also has a product, so you can multiply functions, and the multiplication here is again pointwise. So the trick is always you use the structure that you have in C to give a structure to C of x. So the function is f times g in the point x as the value f of x times g of x. So you multiply the values of the single functions in that point. If you do so, there is a function, the identically equal to 1 function, and this behaves like the 1 for this multiplication. So you multiply it on the left and on the right, you still get the same function you started with. And finally, because the complex numbers have this evolution, the complex conjugate that reflects basically numbers along this horizontal axis, you can actually put an evolution also on this set of functions. And you define the conjugated function f star to be the function that in the point f has the complex conjugate value of the function f in x. Now, if you put all this together, you get that C of x as a structure of a unital star algebra. This is what we call it. But there is more to this, and this connects to the comment that was just made about norm algebras. C of x comes with a norm. This norm is defined to be it's the infinity norm. If you've seen it in analysis courses, is the supremum of the values that the function f obtains on this set x. And with respect to this norm, C of x is a Banach star algebra. So star algebra, I just told you this is what happened before. And Banach just refers, well, we're here in Poland, so you know who Banach is. Banach refers...
It's a Banach center, we are.
Exactly. So Banach means that the space is complete with respect to the norm above. And finally, and this is a very special identity, and that's why it deserves to be in its own box, is when you look at the norm of the product function f star f, this is actually equal to the square norm of the function. And this is something you have in complex numbers, and you actually define the norm of a complex number to be z bar z. But this is a very important result, and this makes that C of x as this additional property that turns it into what is called a C star algebra. So there are various sister algebras out there. Let's look at a very simple example, discrete space. We have endpoints. Then if you look at continuous functions on a discrete space with complex values, then this is the n-dimensional complex vector space. So we can take the vector space structure that we have there. We can take coordinate-wise multiplication to give it an algebra structure, complex conjugation to make it into a star algebra. But then we have to be careful the way we define the norm, because if we want this equation here, we cannot take the usual norm that you have on Cn, the Euclidean norm. We look at the maximum norm. And after all, that's how I define it on C of x, right? I looked at the supremum norm. So if you use the maximum norm, then C of x, so in this case, C to the power n is a C-star algebra. And this is important that the norm is not the Euclidean norm, because there is an important result in C-star algebra theory about uniqueness of norms in C-star algebra. So there is a unique C-star norm. There is a unique norm that makes this identity. Okay, so why are we interested in commutative C-star algebras? Well, from my perspective, it's because they're very nice, nicely related to spaces. And indeed, we just saw that from a space, we can construct a C-star algebra, but now you can go the other way around and show that every point in your space gives you a functional on the algebra C of x. So remember that the functional is a function defined on functions. I mean, it's a bit of a weird way of putting it, but the idea is that this is an object that goes from the space of functions, C of x, into the complex numbers. And we define this sigma p acting on the function f to be functional that gives you the value of the function in the point p. So for every function, we get some value. And now this is compatible with the product structure you have in C of x, because when you apply sigma p to f of g, this means that you look at the value of f of g in the point p. And we saw that the f of g in the point p is defined to be the product of the values of f and g in the point p, which is nothing but sigma p in f times sigma p in g. And if you do it for the function identically equal to 1, because this function is identically equal to 1, it will have the value 1 also in the point f. So this tells us that this object, sigma p, is a character or a pure state, if you're more C-star algebraic, on the algebra C of x. And what is important is that all characters of the algebra C of x are of this form. You can prove this. And what is even more striking, if you look at the set of the characters, this actually comes with a topology that I'm not going to elaborate on here. It's a weak star topology. And this gives you that the space of characters on C of x is actually homomorphic to x. So it is the same topological space as the space you started from. And this is striking. So you basically you have a space, you construct a C-star algebra, and then from this C-star algebra, you can reconstruct the space by looking at the set of functionals. And this is an important result that is due to Gelfand, which is that any commutative unit of C-star algebra can be realized as the algebra of continuous functions on some space. And this space is constructed by looking at the character on the C-star algebra. So not only every space gives you a C-star algebra, every space gives you a commutative C-star algebra, but every commutative C-star algebra, unital, gives you a compact topological space such that the algebra itself is the algebra of continuous functions on the space you construct out of characters.
Francesca, just one quick comment. This is in the paper of Gelfand and Neumann, this claim.
Really? Oh.
Yes. But you see, the thing is that it's called Gelfand transform because Gelfand did all that stuff for Banach algebra, but he somehow couldn't close the loop. He couldn't come with this final conclusion, and because he missed this assumption about Banach algebra being a C-star algebra, because this claim is false.
This doesn't work for Banach.
Exactly, this claim is false for Banach commutative Banach algebra.
So it's in this Normiotering.
Because you can have some self-adjoint nilpotents and you have a commutative Banach algebra, and then this is not any function algebra, but indeed this equivalence of categories is in the paper of Gelfand and Neuberg in 1943.
Yeah, thanks for pointing that out. Should change my slides then. So now we can do something fun. Well, I don't know. Mathematicians like to remove hypothesis and see what happens, right? So instead of looking at commutative unit of C-star algebras, we just drop a couple of assumptions and say that a C-star algebra is a Banach star algebra. So a star algebra that is complete with respect to the norm, with the property that the norm of A star A is equal to the norm squared of A. So this is precisely the identity I showed you before as its C star identity, and now this is a general C star algebra, commutative or not. There are many nice examples of C star algebras that we encounter in mathematics, and the first one is, and now we go back to matrix mechanics, the algebra of n by n complex matrices is a C star algebra, and the algebra structure is the obvious one. So it is a vector space, and it has multiplication, a non-commutative product, unless n is equal to 1. And the norm that turns it into a C star algebra is again the supremum norm, or if you want, the operator norm. So this works for a man of C, so you can generalize it to infinite underlying dimensions. So the algebra of bounded operators on a Hilbert space with the operator adjoint, so with respect to the inner the Hilbert space structure, and with the operator norm, which is again this one, is also a C star algebra. And inside this B of H, there is a non-unital C star algebra that forms an ideal, and that's the algebra of compact operators, which is the limit of the matrix algebras, Mn of C, when you can approximate compact operators by finite rank ones. So now again about B of H, this algebra of bounded operators on Hilbert space, this is really the prototypical example of C star algebra. There is an important result, which is GNS theorem. I mentioned briefly before the GNS construction in one of the questions. It says that whenever you have a C star algebra, then you can always find a Hilbert space and an injective star homomorphism. So an injection that preserves the C star algebra structure from the algebra into the algebra B of H. So the algebra of bounded operators on the Hilbert space. Now this theorem is non-trivial, but it is constructive. It tells you how to construct this Hilbert space. And it has the important consequence that whenever you're talking about a C star algebra, you're talking about something that can be embedded into an algebra of bounded operators on a Hilbert space. And this you can say, in other words, by saying that every abstract C star algebra, so a C star algebra in this definition, is actually a concrete C star algebra that is a subset of B of H. And this is basically the foundation of the field of C star algebras and non-commutative geometry and those operator algebras. So let us go back to our quantum mechanics, and this may connect to the previous question again, is now the cat is very happy because he has a subalgebra of B of H. Now this in this setting we have the bounded, and now there will be some discussion about this, bounded observables of a quantum mechanical systems are just self-adjoint elements in a C star algebra. Self-adjoint meaning that when you apply the adjoint twice, the adjoint that you have in the C star algebra, you get the same operator. Then now the states of the system are the states of the C star algebra, so they are normalized and positive linear functional on A. And now if you perform a measurement, the value, okay, I wrote something silly here. I meant the value of an element A on a state omega. Yeah, sorry, F and C, you see, this shows that the language is non-commutative. I swapped F and N and I got something wrong. So the value on a state omega of an element A in A is the expectation value of the observable for the quantum system in that state. So observables are operators. When you apply the state to the operator, you get a number. This number is real because A is self-adjoint, and this number is the expected value, the expectation value of the observable on this particular state. So if you then take A to be B of H, then bounded observable are just the bounded self-adjoint operators, and then look at a unit vector in H. This gives you a state on the algebra by just defining the state as the inner product of psi A psi. So exactly what we did in the Dirac formalism. We measured the values of the observable by taking this, we called it sandwich when I was studying quantum mechanics. I think it's a good description of what this thing does. So we put A inside a sandwich with bread made of psi. So this is basically the way that the axioms of quantum mechanics were described by von Neumann. So it's a translation from the setting that I wrote before, that I described before with only Hilbert spaces into C-star algebras. Of course, if you're a 10th year, there was a quick remark before by Piotr saying that P and Q have to be unbounded if you want to represent them, you know, on a Hilbert space. So this makes it here we may be in trouble. The truth is that we are not in trouble. So let's have a look at the canonical commutation relation, and let's look at them on the real line. So P in Q minus QP is minus I divided by H bar, and here it's P is a multiple of the differentiation operator on R, and Q is a multiplication by the position, so by the variable that you have on R. Now, as said, this equation cannot be solved by bounded operators. The two operators that I just mentioned, position and differentiations, are a bounded operator. However, what you can do is the following trick. You can exponentiate the equation before to a one-parameter group, and then you get what is called the Weil form of the canonical commutation relations. This tells you that the operator e to the ITQ times the operator e to the ISP. And I will say in a second what I mean by the exponentiation here is equal to the constant e to the minus ist times e to the, well, actually this depends on s and t, e to the isp times e to the itq. Now, when I say that I take an exponential of an operator, I'm just using the fact that my operators are self-adjoint, so I can make sense of a formal power series in those operators. And conversely, whenever you have a one-parameter group, U and V, sorry, we have two one-parameter groups, U and V, that satisfy a relation like this one, then inevitably these operators come from this commutation relation. So they give rise to a family of operators that satisfy this condition here. So the fact that the axioms of quantum mechanics of von Neumann are described with sister algebras that are bounded objects is not a problem, because we can always use this Weil trick to move from unbounded operators to bounded ones, and then this will give us solutions to the canonical commutation relations. And it is
so in other words, you can apply logarithm to the boxed equation to get equation number 2.
Basically, yes. Yeah.
Okay.
Although the logarithm is a nasty function. Yeah. So
between inverted commas.
Yeah. So, and there is an important theorem, which is the Stone-von Neumann theorem, that tells you that the way you solve this equation is unique. So actually, when you think of differentiation and multiplication as the operators describing position and momentum on R, well, they are the operators that solve this equation. So it's really all very solid. Okay, so now let's move to non-commutative geometry. So non-commutative geometry is a general mathematical framework that was introduced by Alain Kohn, Fields medalist in the 80s, so around the time he got the Fields medal. And this is inspired by non-commutativity of quantum theory that we just observed, but also by this gap-found duality that I showed you just now, which tells you that if you look at a topological space, you can construct a commutative sister algebras of operators, and there is an equivalence of categories. So looking at the algebra or looking at the space is equivalent. And now what we do in non-commutative geometry, as I said, we like to drop a hypothesis and see what happens, is to think of non-commutative sister algebras as some non-commutative space. What does it mean? Well, it's a non-existing space, because if it were a space, the algebra would be commutative, but it's a framework for studying certain problems that appear in geometry, especially using a language of functional analysis, and see whether this can bring some insights. And it does, actually. So I see that I'm running a bit out of time, so I will just give you some example, a very basic example of a commutative space and of a non-commutative one. So I would like to start with the most simple compact topological space that has some topology, which is the circle. You can think of the circle as the unit vectors in the complex plane. And then you can describe the sister algebra C of S1, the continuous function of S1, in various ways. And if you know algebraic geometry, you can think of it as a space, as a polynomial algebra. So you look at the Laurent polynomials, and then you close in some norm, because we want the norm to be able to apply the Dirac-von Neumann theorem. And if we represent this algebra on a Hilbert space, there is a canonical way of doing this, which is to look at the space of square integrable function on the circle, which by Fourier transform are actually the two-sided sequences on the integers. Now, Fourier transform gives an isomorphism between these two Hilbert spaces. So if you look at the operator that multiplies by the first Fourier mode, so by e to the 2 pi I theta, then this is and if you look at the orthonormal basis given by the Fourier modes in L2 of S1, this basically becomes in the orthonormal basis that you have for L2 of Z, a shift operator. So when you multiply by e to the 2 pi I theta, you increase by a 2 pi period, which is the same as moving from the Fourier mode with label n to the Fourier mode with label n plus 1. So this operator of multiplication is actually what is called the bilateral shift, because it has an adjoint that just does the opposite. It takes basis vector en and maps it to en minus 1. And you can claim and prove very easily that the C-star algebra of C of S1 is the smallest C-star subalgebra of the bounded operators on L2 of Z that contains this unitary. And of course, it will be a commutative C-star algebras because of this. But you can also see it here when you do U star and you do U star U, you get back the same. You get the same object. You actually do get the identity. So this is a very simple C-star algebra, and it's well the simplest interesting topological space. You can do something slightly more interesting if you change the Hilbert space on which you're working. So instead of looking at two-sided sequences, you look at one-sided sequences. So you look at little L2 of n, which means that you have what in physics is called a vacuum vector. You have a vector that is the first vector in your infinite collection of basis vectors for your Hilbert space. So you define this operator that I call T now to distinguish it from U, and it takes En and maps it to En minus and En plus 1. And it also has an adjoint. Of course, we're in Hilbert spaces, there are adjoints, and it does what you expect it to do. It lowers the index. Of course, there is a problem there, because if you're already at the lowest possible level, you cannot go lower because you only have indices in the upper part. So for positive integers. So in that case, the operator has value 0, so it means that it has a kernel, but it's a one-dimensional space. And now you can do the same trick as before and say, okay, I'm interested in this C-star algebra that is generated by T and T star. Well, this C-star algebra is called the Toeplitz algebra, and it is a non-commutative C-star algebra, because if you do T star T, since you first apply T and you raise the level, let's say, you can go back, and this gives you actually the identity, because En goes to En plus 1, and then you go down to En. But if you do it the other way around, this is almost always the identity, except for when you start here, because T star will give you 0 there. And this you can summarize by saying that TT star is 1 minus the projection onto the kernel of T star, which also happens to be the span of E0. And now, this was mentioned before, this is a finite rank projection, and limits of finite rank projections are compact operators. So if you were to take powers of T and powers of T star and multiply them, you would, and then look at the algebra that contains all of these objects, then you will see that these operators will commute up to a compact operator in general. And this you can write if you're a fan of extensions, if you're more algebraically minded. Like this way, you say that the T is an extension of the commutative algebra C of S1 by the compact operators. Or if you want, the elements of T commute up to compact operators. And when they do commute, inevitably, you remove this part, you get the commutation relations that we saw before. So you get the continuous functions on S1. This is a very important theorem. It's Coburn and others, and it has many consequences, including index theorems and other important results in the theory of C-star algebra. And if you want to apply this philosophy that I mentioned, that non-commutative C-star algebras should be non-commutative spaces, then you can think of C of S1 as a circle that is the boundary of something. Classically, it's a boundary of a disk, and here it's the boundary of this algebra that is not a space, but behaves like a space. This algebra is often called a non-commutative disk. And yeah, it's really what it is. if you compute the spectrum of the sister algebra, is something I haven't mentioned, but it's the analog of this topological space that we constructed when doing Gelfand duality. Then the spectrum of the sister algebra is a disk. So there is a topological space related to this sister algebra that looks like a disk, but the sister algebra is non-commutative, so there is no Gelfand duality here. Okay, and I guess I will skip on this part, but well, maybe I'll go quick over this because you saw some of this. The interesting thing about non-commutative geometry is that it also generalizes an important theorem from the 20th century, which is the Atiyah-Singer index theorem, which tells you that, well, that the indices of Fredholm operators can be computed in purely topological terms. And there is a theory which is called K-theory, which is was developed by Grothendieck and Atiyah, Hirzebruch, and many others, which is a theory that studies vector bundles on spaces, or in the algebraic setting, finitely generated projective modules on sister algebras. The reason why we look at these finitely generated projective modules is this other important duality theorem, which is the Serres-1 theorem, and which tells you that if you have a compact Hausdorff space, so you're in the setting of the Gelfand duality, and you look at the objects called the complex vector bundles, so they are just collections of vector spaces parameterized by your underlying topological space X in a way that is several compatibility relations that I'm not going to write here. Then out of this vector bundle, you can construct something algebraic, which is a ring, and actually it's also a module over C of X, which is the sections of this vector bundle. And this is a finitely generated and projective module, so it has these two properties that make it kind of finite dimensional, reflecting vector bundle structure. And conversely, whenever you have finitely generated projective module, you get that it comes from a vector bundle. And this is like taking Gelfand duality to the next step. So taking it to bundles, vector bundles. It tells you that they're looking at vector bundles or looking at modules over a commutative sister algebra is exactly the same. And this is what has allowed operator algebras to generalize important results in index theory to the world of non-commutative algebras. But the even more interesting thing is that you can use the existence of such a theory, of K-theory, to explain various interesting features of our world and our physical world. And in particular, there are models of solid state physics that can be described in a completely operator algebraic terms by constructing a Hilbert space and a Hamiltonian operator with a certain symmetry. And this explains some features of solid state models where we observe quantizations of certain quantities, and the quantization of those quantities comes from computing K-theory pairings for sister algebras. So it's an interplay that's between algebras taken as models for physical systems, and this inevitably gives you quantization of quantities. So here, this may sound all mysterious terms for you. We're talking about a Fermi unitary, and I'm talking about winding number of a unitary, but these are just mathematical terms for describing currents that I can measure in certain materials, and that those currents turn out to be quantized. So, like I said before, to have values that are integer multiples of a fixed value. And the reason why this is the case is because we're dealing with operators, and these operators have discrete spectra, and then there are invariants, topological invariants, that gives us exactly the discretization of those quantities. And if you want this equality that I wrote here, this identity of two invariants of some physical system, is actually a consequences of this exact sequence that I wrote before, this Toeplitz extension, which is a very elementary sequence of sister algebras. It just involves two of the most simple sister algebras that there are, the functions on the circle and the function on, well, the Toeplitz algebra, so this non-commutative disk. Now, this may sound a bit speculative, but it's really an area of research that is being very successful at the moment. Is using techniques from non-commutative geometry, and in particular K-theory, to explain some interesting observation that in solid state physics. And this is again yet another instance of this unreasonable effectiveness of mathematics, and in particular of the field, I would say, of this field operator algebras in describing the world around us in a way that is rigorous and compatible with experimental observations. So I'd like to conclude with this, with leaving you with this quote by Eugene Wigner. I hope you can all read it, but I will also read it for you. The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift, which we neither understand nor deserve. We should be grateful for it and hope that it will remain valid in future research, and it will extend, for better or for worse, to our pleasure, even though perhaps to our bafflement, to wide branches of learning. And now this is only for quantum mechanics, but as you know, mathematics explains many phenomena in the world around us. So I think we can really enjoy having this, receive this gift, whoever or whatever gave it to us. Maybe just God created the integers and then we did the rest. I don't know. So thank you for your attention.
Thank you so much, Francesca. Okay, Adam.
Okay, so I would like to ask a question about the spectrum of this Toeplitz algebra. Is it correct that I understood that you said that the spectrum is just a disk?
Yes.
Okay, so in fact, it is Hausdorff, yes, which is very exceptional for general sister algebras.
Yes.
Okay.
That's correct. Yeah.
Okay, thank you.
Yeah, so it's very special of this, but of course it also gives you an intuition of kind of the dimension of this algebra. And if you would do it for other Toeplitz algebras, like the Arveson algebra, then the spectrum there is also well, it's not a disk, it's a ball in CON. So it's really, this algebra is something about boundary extensions and so on.
Okay, maybe one more question, since quite recently I learned that this Toeplitz algebra also appears in this context of deformation quantization, where people try to somehow do it not on a formal level, but do it more strictly
Yes.
on general, as far as I know, the most broad framework is the framework of Keller manifolds, something like that. So could you somehow comment on this? What are the expectations?
Well, it's a very interesting question. Yeah, so, well, indeed, the Toeplitz algebras are used a lot to quantize quantities because they naturally lead you to this world of differential operators. And so I think it's a very interesting well, idea, but I also think that it's been around in the literature for a while. So now I'm asking you all for help because you're in Poland. So there was this organizer of the Białowieża workshop that unfortunately passed away this year.
Ogiewicz, yes.
Yeah, yes, so some papers on using Toeplitz algebras for doing quantum physics. So this is also a place where you could have a look.
Okay, thank you.
You're welcome.
I have a small follow-up on the question from the very beginning of the talk concerning measurement. So, as I understand, if you measure, you interact, but there is no Hamiltonian, no interaction, no evolution of this process. So somehow it's like I don't know, not in this. It's not described. Yes, it's like some classical thing is interacting with the quantum one. Can you offer a?
Yes, indeed, here in what I described, there is no, no time evolution. So it's really just a pure act of measuring a quantity on a given state. Of course, then when you introduce also time evolution, that things even complicate even more, because then you have all these time energy commutation relations. But yeah, indeed, in this model, I'm just looking at purely at two observables that are defined on some Hilbert space. and then turn out to be non-commuting, so they cannot be simultaneously diagonalized if you want, and this has the consequences for measurements. But yeah, in what I described, there is no time evolution, it's correct.
So there's no theory of measurement, quantum measurement.
Well, if you want, yeah, because the time is not, yeah, so we can enter the, yeah, this becomes, of course, a philosophical and technical discussion about the notion of measurement, right?
Thank you.
Okay, so this question may be a little bit off topic, but I've heard that the mathematics of quantum electrodynamics is built on shaky foundations. And could you maybe explain like what's the problem in general, and can maybe
that's really not my area of expertise, but if there is someone either online or in the audience that wants to say something, I will be happy.
Well, I can offer the following explanation. I mean, it's a saying that first quantization is a miracle, the second quantization is a functor. So, yeah, mystery, sorry, yes. Yeah, so first quantization is a mystery and the second quantization is a functor. So somehow, yes, indeed, what you mean by, might mean by shaky grounds is not that there's anything wrong with mathematics there. It's just the question of how we say that we take this classical world and we quantize it. Okay, here's some classical mechanical system and we want to quantize. And here we run into problems because say, imagine that you have some phase space and your variables are position and momentum. This is the classical mechanical phase space. There's a lot of mathematics going into the usual mechanics and beautiful kind of differential geometry, if you wish. And then we want to say, all right, but these P's and Q's, position momentum, no longer commute. So we have some functions in P and Q, some that have physical meaning, and we want to assign to them non-commutative operators. But how do we do it? Because when we have a function which is a polynomial, and it doesn't matter whether we write P squared times Q cubed or the other way around. And it's getting complicated when you want to replace it by unbounded operators. So there are some recipes how to quantize it, but it's a mystery. But then when you go to second quantization, it's also formalized. It's basically a functor. So that's probably what you referred by shaky foundation. The process of quantization, assigning sort of quantum mechanical systems to classical mechanical systems. That's how I understand it. But again, I'm not a physicist, so I don't know.
So maybe you meant this shaky foundation, meaning that there is a problem of renormalization, so getting rid of infinities. So indeed, what can be done rigorously is this free field theory, the quantum field theory, where there is no interaction. And for this theory, everything is fine somehow. But when even the simplest interaction came into play, then there is a problem how to formulate it correctly. And there is a whole big business of constructive quantum field theory. People manage to construct some models in 2 and 3 dimension, very simple, like a toy model, but there is no a single one constructed in 4 dimension. And physicists, okay, quantum field theory is in the space-time, so we are interested in the 4 dimension. So maybe this is somehow relates to your question.
Yeah, but then it's quantum field theory, not just quantum mechanics. So
yes, but quantum electrodynamics is already at the level of the quantum field theory. It's a second quantization.
That's true. But here, by the way, one might mention, when it comes to the mystery of renormalization, so removing infinities and making sense of calculations, here's a beautiful work in non-commutative geometry of Kohn and Kramer, who proved that this cooking recipes given by physicists for normalization is actually governed by a beautiful Hopf algebra, right? So that's Kohn-Kramer Hopf algebra. Okay, any further questions?
You mentioned bulk edge correspondence, and I wanted to ask, is there a clear way to see what kind of algebra should be chosen for a given Hamiltonian or generally physical system that is studied?
Well, there are several, let's say, candidates. I mean, you can look into the literature. Okay, it all started with the work of Jean Bélissard, but for the quantum Hall effect, and then this has been expanded. And usually it's it's usually a C-star algebra that comes from the dynamics that the Hamiltonian gives you, but there are several ways of constructing it. So people look at cross-product C-star algebras, other more general groupoids. There is also research direction, which is very well represented by Ralph Meyer, and about using row algebras, which are different type of algebras. Comes more from analysis, somehow pseudo-differential operators and so on. So it's really, there are some canonical examples for particular cases, but it's still a field that is growing. So there are many papers surfacing and addressing different models, lattices, or non-periodic lattices, and aperiodic lattices, or even non-periodic mediums. So it's a very, let's say, young field that is developing, and in general, the C-star algebras are in some way associated to the Hamiltonian, but there is not yet a canonical way of doing this.
Okay, thank you. And may I ask if the bulk edge correspondence is somehow similar to, for example, ADS CFT correspondence, and as it is also used in solid state physics in some way?
Yeah, I don't really know what the connection there is, but to talk about something related to ADS CFT, in string theory, there is this T-duality business. And there is some work by Matai and Zhang and collaborators on the interplay between T-duality and bulk edge correspondence. So maybe that could be a way of connecting to the more to the duality world, really. But okay. I don't know if there's any work on ADS CFT and bulk edge in the non-commutative geometry setting. This I am not familiar with, and I'm not sure whether there is such a thing at the moment.
Okay, thank you.
Okay, anybody else from the room? Nope. Anybody from the Zoom? Frank, are you game for a question?
No, currently there's no question.
Okay. All right, so in this case, let us thank Francesca again for a very beautiful talk.
Thank you.
I think this really deserved to be part of baby steps, because that's precisely what you did. You walked us with baby steps, and you gave really the very foundation of non-commutative geometry, our field of research. So combining your talk with spectral triples of Michał, I think that we had a very faithful representation of non-commutative geometry at baby steps. Okay, so thank you again, guys. Thank you, Francesca. I hope to see you here in person in a year at our graph algebra meeting.
Of course. I
yes.
hope so too.
Yeah. And I stop recording, and we resume after lunch at 5 p.m. Okay.
Thanks a lot.
Bye-bye.